Something that I would really like you to embrace in this class is the fact that you can use your periodic table. It is your friend. People often think of the periodic table as their enemy. Chemistry is the only class that you have a study guide on every single test. That is your periodic table. So get to know it really well because it's going to help you. If you know how to read it, it's going to really help make your life easier in this class. So today we're going to talk about the parts of the atom and how they affect atomic behavior and characteristics. We're going to talk about how to read the periodic table. We're going to recognize periods and groups, and we're going to start to classify elements by where they are on the periodic table, so their location. And finally, we're going to begin to memorize some elements. This semester, I will require you to memorize the names / symbols of approximately 30, I think it's about 28 elements. Most of those, or a lot of those, you probably know already. For example, carbon, what's the symbol for carbon? What's the symbol for oxygen? What's the symbol for hydrogen? There you go, you're already partway there. So it'll only be the elements that we are going to really use in this class. Everybody have this down? Okay, just one more minute. Can anyone remind me what the definition of an atom is? We talked about it on the first day.
Smallest
Yes, so the smallest unique particle of an element, it is the, and that it is the uniqueness of that particle that gives the element its properties. So smallest unique particle of an element. For example, carbon is different than nitrogen because of its specific atomic makeup. And so they act very differently, those two elements. So I'm going to ask you for the parts of an atom. I'm not asking for the particles. I'm asking you for the parts of an atom. What's one part of the atom? Those are the particles. Nucleus, yes, nucleus. So parts of an atom, nucleus. A nucleus, let me move this check, is very small but incredibly massive. We have become, in English in general, massive generally means big. Massive actually means very, very heavy in scientific terms. So something can be very, very small and very, very massive. So that just means it's incredibly dense. So the nucleus it makes up 99.9% of the mass of the atom, but a very small part of the volume. For reference, imagine an atom is about this, the diameter of the racetrack at your high school, you know, a quarter-mile racetrack. If that's the entire atom, the nucleus is a pea in the middle of that racetrack, a little green pea, okay? That is how small a nucleus in general is compared to the outside of the full volume of the atom. So atoms are actually a lot of empty space. And what is an atom made up of? Here I want the particle names. Protons and neutrons. And now the orbitals are what's in the orbitals? Electrons. And so they make up the rest of the volume and 0.1% of the mass. So the mass of electrons is almost negligible. It is so small compared to protons and neutrons. And the way we measure the mass of a proton and neutron is something called an atomic mass unit. So an atomic mass unit AMU, is the weight of I would say the approximate weight of 1 mole of protons or neutrons. Does anybody know what a mole is? Yes, 6.02. So 1 mole is 6.02 times 10 to the 23rd of something. It can be 6.02 times 10 to the 23rd protons. It can be 6.02 times 10 to the 23rd neutrons. We can talk about a mole of atoms, a mole of molecules, a mole of people. This number is so big that a mole of people is tens of orders of magnitude larger than the amount of people on Earth right now. We have 1 billion people on the, no, how many? 7 billion people, right? Something like that. Maybe getting up towards 8. So that's 8 times 10 to the 9th people. This is 6.02 times 10 to the 23rd. It is such a big number that it's very hard to conceive of it. And that's because a proton is so small that to measure that, it's almost impossible to measure it. We have very, very, very sensitive instruments to measure that. But if you were trying to talk about a proton, just one proton, it's not an easy number to work with, which is why we have this mole. So we don't have to talk about this in grams. We talk in terms of one proton. We talk about the weight of a mole of protons or a mole of neutrons. And you can think of it as, because it's a number, just a number of something, you can think of it, it's comparable to a dozen of something. So you can have a dozen eggs, but you can also have a dozen people. You can have a dozen cars, right? It doesn't specifically, it's not like you're saying, oh, it's 10 grams, right? It's not a unit that's specific to like mass. It is just a number that you multiply by anything. So you can have a mole of anything, just like you can have a dozen of anything, okay? Now, 1 AMU is an equivalent unit to 1 gram per mole. Okay? So we have another equivalent unit situation that you had to memorize for the last test. What is that? Milliliters to cubic centimeters, okay? So if you're talking about 1 milliliter, it's the same thing as talking about 1 cubic centimeter. That's the same thing with atomic mass unit and grams per mole. So all the weights on the periodic table, you can say it's like carbon is 12.01 AMU or 12.01 grams per mole. It's an equivalent unit. Do you have a question?
Well, I was just kind of thinking, if you can convert it to grams, can you convert it to ml?
What do you mean?
Okay.
Yeah, I mean, here.
Yeah.
Yeah, I mean, yeah, you could do, so 1,000 AMU would be 1 kilogram per mole. Yeah, you could do that. That's not super common. We generally talk in grams when we're talking about chemistry, but yes, you can. Yeah, because and the reason we don't talk about this in terms of just the grams of 1 proton, 1 neutron, because those are about 2 times 10 to the minus 23rd grams. That's just a really small number. It's much easier to say 1 AMU and talk about an amount that you could actually hold in your hand, you know, and conceive of in your hand. Okay. So a proton and a neutron are approximately the same weight. Neutrons are slightly heavier, but we just say that both are approximately 1 AMU. If they're like actually like 1.001 something something, we've gotten more precise in our measurements as we develop our scientific instruments, so we know that it's actually slightly off from 1 AMU, but we just say in this class, we're going to just assign each of those 1 AMU per mole of protons and neutrons. Electrons have mass, but it is very, very small, that we're just going to say that it's 0 AMU because it's like 0.0034 something. You know, it's a very small, it's compared to 1, it's a negligible amount. And this is really where significant figures come in. We're going to talk about how the 1 AMU is one significant figure, okay? So a proton has the symbol lowercase p, and what's the charge on a proton? Positive. Pro means you're positive on an issue, proton is positive, so you can write it as a lowercase p or p plus, and that weighs 1 AMU, so 1 mole, it has a mass of 1 gram. And then, yeah, we have a positive charge. A neutron, you can write as a lowercase n. And what's the charge on a neutron? There's no charge, it's neutral. So you can just write N0, N naught, and that just means there's no charge on it. It's a neutral charge, and it weighs 1 AMU and neutral. And an electron, therefore, has what charge? Negative. And electron written as E minus is something that you will see a lot. This is the most common shortening of these. You'll see some protons, some neutrons, but electrons, because electrons are the easiest to lose and gain because they are in the orbitals. It is harder to lose and gain neutrons and protons because they're in the nucleus. But if it's on the outside, if it's orbiting around, it is easier to exchange with other elements. Oh, sorry, that's 0 AMU. And that's a negative charge. It is very important to understand that the proton charge and the electron charge are equal but opposite, okay? So that means proton and electron charges cancel each other out. So if I have an element with 6 protons 5 neutrons and 5 electrons. What is, first of all, my mass? What is my mass number in AMU? 11. Because you add the two things that actually have significant mass, which is the protons and the neutrons. So that's 5 plus 6. That's 11 AMU. What is my charge? Positive 1. Because for every electron, you have a proton that cancels it out. So you have 5 electrons, and 5 of those protons cancel those electrons out because they're equal and opposite. You have 1 extra proton, so you have a +1 charge. So when you gain an electron, so generally we just gain and lose electrons. When you gain an electron, is your element going to become more positive or more negative? More negative, because it's because an electron has a negative charge. So if this element gained an electron, it would become more negative, it would become 0. And then if it loses an electron, it becomes more positive. So if this element lost another electron, if we had 4 electrons, it would be +2. Does everybody understand that? So it's always, when it comes to charge, electron, if you're going to lose and gain electrons. So the number of protons, I'm going to give you, so I want you to do this one. 26 protons, 23 electrons, and 34 neutrons. Tell me what the mass number and the charge is. What's my mass number? 60. 26 plus 34 is 60. So 60 AMU. And what's my charge? 3 plus 3. Because we have 3 more protons than electrons. So 23 of those electrons are canceled out by the 23 protons, and we have 3 protons left over. That's a +3 charge. Excellent. So protons and neutrons are the only one with mass. So 26 protons weighs 26 AMU, and then 34 neutrons weighs 34, so 26 plus 34. So we don't consider this because this has negligible mass. Yeah. So let's talk about our atomic symbols. What is this number? Yes, it's 19, but what is it? What do we call that? Atomic number. Does anybody know what that means? The number of protons. Excellent. Not number, number. Number of protons. And then, what's this? Our atomic symbol. Does anybody know what this element is? Potassium. That's one of the ones you have to know. So if you already know it, congratulations. And then what is that? Atomic mass. And it is your average atomic mass. Now, potassium can have different masses. That's called different isotopes. We're going to talk about that more on Thursday. But some isotopes occur more often than others. So this number is the weighted average of the atomic masses of all the naturally occurring potassium as we know, which means that most of our potassium is 39, it weighs 39 AMU, but some potassium, a small portion weighs 41, and an even smaller portion weighs 43. So we take the weighted average of all of those and we combine it to the average atomic mass, which means that not every, that it's not, you don't take an atom and it weighs 39.1. There are atoms that weigh 39, 41, and 43 grams per mole, and you take an average of that, okay? So that's not the weight of every atom, it's the weight of the average. It's the average weight of atoms. And this is in AMU or grams per mole. A little semantics here. AMU is generally called atomic mass and grams per mole is generally called molar mass, but I'm not gonna worry about that distinction. Just so you know, atomic mass and molar mass for an atom are the same. This means that if you change the number of protons, what happens? It is a different element. So if you look back, what the example I just gave you with 26 protons, what's that element? Iron. Fe, also one of the ones you need to know. So the number of protons determines the element, which means that if I add a proton to potassium, what element do I get? Calcium, Ca. Also one of the ones you need to know. Your number of neutrons changes the mass. So you can have an element that have two different atoms of the same element, for example, potassium. One atom will weigh 39 AMU, so that'll have 19 protons and 20 neutrons. And then you could also have an atom that weighs 43, still potassium because it still has 19 neutrons, but it has 19 protons, but it has 22 neutrons. So the only thing that changes is the mass of that atom, and that can affect the stability of the nucleus, which is why we have radioactive nuclei. But yeah, so those are called isotopes, and we will learn more about isotopes on Friday. But I just want to kind of introduce that the number of neutrons changes the mass. So it doesn't necessarily change the, it doesn't change the element. And the final thing is what does the number of electrons change? The charge. Electrons are much more easily given and taken away than neutrons and protons. Of course, this does depend on the element. We will learn more about which elements are more likely to give and take protons on Friday. But the number of electrons can change the charge, okay? Because if you have, for example, if you start out with 19 electrons and 19 protons, which is what neutral potassium has, right? Because 19 plus 19 cancel each other out. If you lose one electron, you are now K plus. You are now positive potassium. Any questions on this? No. Okay. Let's talk about labeling the periodic table. So if you have your periodic table, bring it out. You should all have one. Raise your hand if you don't. It will help you if you have multiple colors of pens and pencils. Just saying that's not what I want. I want the other one. Cropped one. There we go. So I have one just like you do up here. This is the table you will have on the test. So does anyone know what a column is called on the periodic table? Columns up and down. Yes. Specifically on the periodic table. A group. Someone said a group over here. So columns are groups. And if you don't remember the difference between a column and a row, you're both horizontally, and columns hold up buildings. Okay. So a column is a group. And groups have recurring properties, meaning that this group will act similarly to each other, okay? And we'll talk more about why that is, once again, on Friday. And then, what are the rows called? It's where it gets its name. It's the period. So, the column are labeled across the table. There are two systems, 1A through 8A, and that is just these two columns and these 6 columns. So these are what are called the main group elements, and those can just be labeled 1, 2, 3, 4, 5, 6, 7, 8, and that's the 1A through 8A. That will help you when it comes to figuring out the number of outside electrons. We will once again get to that on Friday. And then if you want to name all of the groups across the table, you'll go 1 through 18. And so these ones in the middle are called your transition metals. You also have your lanthanides and actinides. So these lanthanides and actinides technically belong right here, right? It's like you cut these out and put them on the bottom, and I'll show you why we do that. If you look at ptable.com is a really good website for you. It will be a really good resource if you don't have this table in front of you. And there's all sorts of properties and everything. However, this is what this periodic table would look like if we didn't take out the lanthanides and actinides. We wouldn't be able to fit it on a piece of paper that's 8.5 by 11. It's just size-wise, it's not the best way to look at it. So, and most people, most scientists even, generally don't work with the lanthanides and actinides. That's a very specialized area of chemistry. So generally we pull these down and we smush these two sides together, and that's why we have this, okay? Now let's go back here. Can anyone give me a name of a group that you know? Noble gases. I heard noble gases. Do you know which of the noble gases? 8A. Yes. So these ones are the noble gases. What? There will be areas, you don't have to, there'll be areas of the periodic table that you'll kind of distinguish. That's when you want to use color. But I mean, if you wanted to color just this column, you could, that'd be fine. But generally you'll be fine with the labels. I'm just using different colors so you can see. What's another group? Halogens, do you know which one that is? It's actually right next, 7A. The first one is one we will have to know, but it's a different. So then we have the halogens. Not halogens. HALOGENS, like a halogen light bulb. So that's group 7A. Does anybody know what this is? Alkaline metals. ALKALI space metals. And does anybody know what this row is? Group is? Alkali earth. Alkali earth and alkali metals are two different things. Alkali earth metals. So don't label beryllium as an alkali metal. It is an alkali earth metal. I would also just accept alkali and alkali earth for those. So I might say on the test, what group is, or give me an example of an alkali earth metal, and you would have to say one of these. There is one thing specific about hydrogen. It's not a metal, and I'll kind of talk about that. So see how it's kind of separated? Your alkali metals actually start with lithium. So I'm going to actually move this arrow. Hydrogen is not a metal, so it's not an alkali metal, and it does act a little differently. Hydrogen and helium are two weird ones that we have at the top of the periodic table that act a little differently than a lot of other elements, just because of how many electrons they can have in their shell. Now, as we go down here, this is our orbital level, otherwise known as an N level. This is, we're not going to go into the different types of orbitals, but what you need to know right now is that as you go down the table, you add one more shell of electrons around your nucleus. So hydrogen and helium have one shell of electrons. Then you go down to lithium through neon, that's a second shell, and then going out. So that is our N level. Oops, let's see. Trying to fit that in. So for example, the N level of calcium is 4. It has 4 levels of electron orbitals. Okay? That's LEVEL, just. So what is the N level of the lanthanides? 6. So remember, lanthanides fit in here, so it's 6. And what's the actinide N level? 7. So don't forget that those fit into that table. There's a few more determinations I want to talk about. And this is the difference between metals, nonmetals, and metalloids or semiconductors. That's 2 names for the same thing. So I will talk about the definition of metals and metalloids, but first I want to just tell you which ones are which. So metals are, everything in the yellow. This is where you might want to use different colors. Notice that most of the periodic table is metals. So now it kind of makes sense that these are called alkali metals and alkali earth metals, right? And then these are transition metals. So there are different distinctions of metals within all of the metal generally, right? But everything, you'll see on your table, you have a kind of dark borderline here. So think of almost everything to the left of that is a metal, just not hydrogen, and then a few of those along that line, and we'll talk about those. So non-metals are hydrogen over here. Don't forget that hydrogen is a non-metal. All of these are also non-metals, all within the light blue. And if you use ptable.com, you'll notice that ptable.com has distinctions, metals, non-metals, and then the semiconductors. It has the same distinctions on that table. So if you don't have this table in front of you, you will still be able to use that. Now, semiconductors, otherwise known as metalloids, are those ones in the middle. There are 7 of them. Boron, silicon, germanium, acetine, antimony, tellurium, and polonium. Don't worry, most of those you don't have to know. A couple of those sound familiar. What do we use them in? What do we use semiconductors for? Microchips, electronics. And the reason for that, we will talk about in a couple minutes when we talk about metals and what metals are. So I'll let you all finish notating these distinctions. So once again, this table without all the notation is what you're going to get on the test. You will have to be able to identify which elements are semiconductors, which are non-metals, and which are metals. Okay, so if I ask you to tell me whether acetine is metal, non-metal, or semiconductor, you will have to know that it's a semiconductor. And we will do even more note taking on this table on Friday, because there's more stuff to know. Everyone got this down? Okay, I'm going to go back to taking notes on the whiteboard. What's the definition of a metal? What's one characteristic of metals? What? Luster, otherwise known as shiny. So, if something is shiny, it's probably metallic in terms of the element, just the element. That's why we like our metals. Palladium, gold, silver. We like those things. They shine. They have luster. What's another characteristic of metals? Conductors of heat and electricity. Without going too much into detail about the orbitals of metals, they are able to share electrons very, very easily. So if you have a chunk of metal, or for example, a wire, and an electron moves from this end to that end, it is very easy for that electron to hop from one atom to the next, okay? So electrons move very easily among metals, and that is why they conduct electricity. Most nonmetals, the whole reason they're called nonmetals is because they tend to not conduct heat or electricity. And what's the final thing that is characteristic of a metal? Malleable and ductile. Malleable and ductile are just two different words for how you can manipulate something. Malleable means you can hammer it flat, and ductile means you can bend it, okay? It's just two different types of stress. And so metal tends not to be brittle. It can be bent and it can be hammered flat. That is a characteristic of metals. Semiconductors, so non-metals tend to be none of these things. Semiconductors are somewhere in the middle, which is why we use them for electronics. Because if you had something in your electronic that was a conductor that was really easy, you'd have electrical impulses like traveling through the whole time. And that wouldn't necessarily work. We only want electrical impulses to travel through our electronics at given points that we can control. Semiconductors are in that level where you can control when they conduct and when they don't. Okay, so that's why we use them in our electronics. That's why we have Silicon Valley. Silicon is a semiconductor. We use them in electronics. Electronics are developed in Silicon Valley. A lot of them. Questions? All right. I'm going to tell you the elements. We're going to end a little early today because I want to get all of your exams out, and this is as far as we went in class, but there's one more thing I want to tell you, and that's all of the elements you have to memorize. So these must be memorized for the quiz and the next test, which is in a few weeks. Flashcards are really good for this. So what you need, the ones you need to know, let me see if I can find the full list. Here we go. It's not the whole periodic table. Okay. 3, 6, 9, 12, 15, 18, 21, 24. 27, yep, 28. These are the elements we will most commonly use in this class. Right. And once again, many of these you already know. So you should be able to identify the element from its symbol and vice versa. If I give you lead, what's the symbol of lead? Yeah, EV. So there are some ones that are the symbols that are not directly related to the names. For example, lead. Lead used to be called bum, which is maybe Latin. Yeah. And so there were certain people calling it lead, some people calling it Plum Bum, and finally the scientific community decided on that. So, but we still have the evening session. Gold and silver are the same way, and tin. Do not confuse tin with titanium. Ti is titanium, Sn is tin. So that is something you need to know. This will actually, once you memorize these, it will make your life so much easier in this class, because not only will you memorize them, you will be able to find them on the periodic table more easily. Okay, I'm going to, so we have a worksheet, and I am going to, we always have a worksheet on Wednesdays. I am going to pass out the exams while Chris helps you with your worksheet. This is when I really start to get to know your names when I'm passing out exams. So if I call your name, raise your hand, make sure you double check that it's yours. A couple people yesterday thought they heard their name and got the wrong exam. So just double check that I'm giving you the right. You know, some of you I already know, but a lot of you I don't yet. So forgive me, and I'll do my best with all of your names. All right, but that is the end. What I'm going to do is